Hello, welcome back to the solid state physics class. And in this class, we are going to expand upon the idea that we discussed last time. So, let us discuss a little bit about what we discussed last time. So, I think we discussed uh, a lot about Sommerfeld model and how it is different from Ruday model. And we also modeled some systems according to Sommerfeld model. So what we model? We did very simple two models. We did a model of uh, a confined box. So box boundary condition where the wave function can only live inside a 3D box, and it can't go outside the 3D box. So the wave function is zero outside the 3D box. But I think we also discussed about the periodic boundary conditions. So for the periodic boundary conditions, the boxes are repeated in all of the three directions. So like for example, in the XYZ the directions or the XYZ 3D space, if we have a cuboid, then the XY planes of the cuboid will have the same value of any quantity. For example, so we let us do a little bit of recap of what we did. So first of all, what we did is the box boundary condition, or maybe it can be also said to be um, infinite. It is also said infinite quantum well, because the potential outside the box is thought to be infinite. That's why there is no wave functions there. And so the psi is equal to 0 at the boundaries, right? And we also had this cuboid stuff, like this periodic boundary conditions. Okay, and here what we had is 0. For example, let's say Lx, this is Lx, this is towards x direction, this is Ly, and this is Lz. So we had psi of 0 comma x comma y equals to psi of oops, psi of x comma y comma 0 equals to psi of x comma y comma Lz. So similarly it is for the xy plane, these planes, but we also can have this for other planes because of the same boundary conditions. So this green planes or the blue planes. So the blue planes will be the YZ planes, and the green planes will be the the blue planes will be the XZ planes, and the green planes will be the YZ planes. So these are the two things we discussed Sommerfeld model about. And what we figured out from this when we talked about Sommerfeld model in these two systems, what we figured out is it gives us pretty similar results, pretty similar results. For example, the total energy, the ground state energy of the system, and there are some other quantities which are pretty similar no matter how we define the boundary conditions. That means that there is something more fundamental in Sommerfeld model, right? So now we are going to discuss a little bit about how to more formally approach Sommerfeld model and how to define something else. So like now we are not going to do free electron Sommerfeld model for models like other different boundary conditions, but what we are going to do is uh, invest in something more fundamental. So something more fundamentals about the Sommerfeld model and how upon them we can build the more complicated models. And the most important of them is thermal excitations. And through that we can actually explain thermal and electrical conductivity. And we will see that they give better results than Ruder model, and all the things that we have theoretically told that okay, Ruder model does this, Sommerfeld model does this, we will be having a mathematical understanding of the same. So before that, we will do two things in today's class. One is the second quantization picture of Sommerfeld model, and the second one is we will do what is the density of states, the concept of density of states. So we will learn two concepts in this class. So why do we need Sommerfeld second quantization? Why second quantization? So, and what is second quantization? So what is second quantization? So I will give a very brief introduction of second quantization in this lecture, but I don't expect anyone to understand fully from this small lecture that what is second quantization. So second quantization is a very big concept, but I will give you a very brief and functional description of second quantization that will be enough for us going forward. So second quantization and first quantization. So first quantization is like mostly regarded as the birth of quantum mechanics, because quantum mechanics itself is about quantizations. It is about quantizations of different properties or different quantities of the system. So that is often called first quantization. So the first quantization is, for example, you have some system. You want to measure, let's say, the energy. For example, the energy is the most common measurable object. So then what we do is we have like quantized levels of energy, quantized energy levels. And uh, so we can also describe that, for example, there are n particles in this whole system. So what we can do is we can say that, okay, fine, there are n particles, so the total wave function of the n particles are like they are a function of the individual particles. Here the particles are distinguishable. The particles are distinguishable. So what we need, what informations do we need? In which state is each particle? Okay. But what is second quantization? Second quantization is a language of quantum mechanics when the field, the wave function itself is quantized. So what does that mean? That doesn't mean like we are not going to talk about jargons, but like loosely what it means. It means that when we are talking about indistinguishable particles. So for example, in the previous case, we were talking about n particles, right? For the n particles can be n electrons, they can be n nuclei, they can be n protons. But in real life, electrons, protons, these things are like indistinguishable. For example, there are two electrons, 1 and 2. You can't mark them. So you will not be able to actually understand that that which one is which. If you just exchange them or something, then there is no way to tell that which one is which. So that is why it's called indistinguishable. For example, we have n electrons and they are indistinguishable. So if they are indistinguishable, then the whole physics will change, because now what we talked about in first quantization, that we want to know each state of the particle, each particle, right? But if the particles are indistinguishable, then knowing which state is like each particle in, it is an overkill, right? So this statement becomes an overkill. Here what we will do is we will rather consider how many particles in each state. So there are two different questions we are asking. In one of them we are very concerned about each particle's individual state, but in the second part we are not concerned about what the each particle is doing. We are concerned about how many particles are there in each level. That's it. Basically we have let's say we have the energy, discretized energy. The only way the system can differ is by the number of particles that are in these energy levels. So for example, there are four energy levels. So a very simple example of understanding what is the difference between first and second quantization is as follows. So what we can do is, let's say we have four levels and we have four particles A, B, C and D. So if in first quantization we want to know that what is the state of A, what is the state of B, what is the state of C, what is the state of D. So psi of, let's say, A, B, C, D will be psi A of A, psi V of B, some function of all of this size, all of these wave functions. But if A, B, C, D are indistinguishable and we have four states, then like they are just dots. We don't care. Actually we can't even like extract the information about how is like each particle occupied in some state. So like because they're indistinguishable, so the only permutations or only possibilities for this is basically how many of them are in state 1, how many of them are in state 2, how many in state 3, how many in state 4. So for simplicity, if you consider only two states, then the different possibilities will be 0, 4, 1, 3, 2, 2, 3, 1 and 4, 0. But if we had two states and four different particles, then there will be a lot of possibilities. But here in second quantization, when we are only dealing with indistinguishable particles, there are only five possibilities. So that is what is basically the difference between first quantization and second quantization. Second quantization is a like subject, or it's a language used for indistinguishable particle, where we don't care about what the individual particles are doing. Rather we care about in each observable state how many particles are there. So that's a different in mindset, or the different in like point of view, or like would be a better way to express it, that we are not talking about each state, each particle. We are not interested. Now we shift our interest, or our like point of view, to observables. We want that how many particles are in each observable layer. So that is the second quantization. In second quantization, what we basically, the how the language works is, let's say there is a state A, there is a state 1, there is a state 2, there is state 3, there is a state 4. So what is done is, in if we do, let's say this is a ground state of the, if this is a ground state of the system, if we act the ground state by psi 1 dagger, this is called the creation operator. Then what is happening is, there is one particle which is created at state 1, and if we act on this state, for example this is state number 1. Now this we got this to be state number 1. Psi of 1 is called the destruction operator. Then what we will be done is, the particle will be destroyed, so it will go back to 0. So there might be sometimes some proportionality constants, they will be taken care of by normalization of the ground state or the one state. So but the main idea is this: so you can create a particle in a energy level, or any quantized level, or you can destroy it. You can create a particle having momentum k, you can destroy a particle having momentum k. You can create a particle at position r, you can destroy a particle at position r. So it will look like psi k dagger, psi k creation of particle and destruction of particle at momentum k, psi of r, psi of r. So similarly for position r, So any state, for example, there is a state A which has like multiple properties. So there will be psi A and there will be psi A. So that is how we do the second quantization. So in this case, the Hamiltonian is often given as the Sommerfeld Hamiltonian in second quantization. Is given as Ek sigma, Ck sigma dagger, Ck sigma. So basically, what is this? What does this tell us? This is basically telling us that um, this is how the Hamiltonian is represented. So okay, let me uh, so this thing is called the number operator. So if you actually do this to any system, for example some system A, some state A, it's like a many bodies state A which has like contribution from all of the indistinguishable particles, then it will give you the number of particles that were there in the state having position momentum k and spin sigma. Okay, so this is like, that's why this Hamiltonian is defined like this. So it's basically summing over all the energy levels of all of the states which are like k sigma states. Sigma is the spin, k is the momentum. So it is basically summing over all of these states, and the weights are obviously individual eigenvalues, energy eigenvalues. So if there are n k sigma state electrons here, then it will multiply with this and add all of these up. So it will calculate us the total energy. It will give us the total energy, obviously. So that is the Hamiltonian of the Sommerfeld model in second quantized picture. Okay. So now that we have this, it's a in this case, like this is called the canonical ensemble. So that's again a jargon, but what it means, it's like not important. This name is not important. Particle or electron number is conserved. So that is what it means. But generally, in practical systems, electron number is not conserved. Electron can actually leave the system, or electron can come to the system. So that's if we do that, then the whole this thing, the whole Hamiltonian will actually become this. What is mu? Mu is called a chemical potential. So it basically means that all of the electrons that we are bringing into the system, they have some energy mu already. So if you are if you are taking an electron from mu energy, then putting it into some k epsilon k sigma energy, then the energy you need to do that is the energy you are adding actually in total is this. It's not all ek sigma, but it's ek sigma minus mu. So basically that is what we are doing here. So this is called the grand canonical ensemble, where we can actually bring electrons or dispose electrons to a bath of electron bath, which where all electrons will have energy mu. Okay. But these ck sigma, this is only electron creation operator. But what about holes? Because when what happens in Sommerfeld model, right? So an intuitive explanation of this, or intuitive visualization of this, is there are electrons all over the place. This is the Fermi sphere that we talked about in the last class. This is the Fermi sphere. The electrons which are on the top, or electrons just below, they can actually get promoted to an empty state. So now how does this state look like? The state looks like now. Oops, the state looks like that, as if there will be a hole created here and there will be an electron created here. So that is how the ground state will change. So this will become an electron and this will become a hole. Hole is basically the absence of an electron. So that is how the state will change here. Okay, so now if we say that, okay, fine, creation of hole equals to annihilation of electron, right? So if you annihilate an electron, there you get hole. So let's say we define the whole creation operator. Actually, whole creation operator will be ck sigma, because it will be the annihilation, the electron annihilation operator. So why are we doing this? Why are we like interested in about the holes? Because the excitation of a system can also be hole like. It can be removing an electron, it can also be adding an electron, is also exciting the system. Removing an electron will also excite the system. So the excitation can go both ways. So we define something like dk sigma equals to ck sigma dagger if epsilon k sigma is greater than mu, and ck sigma if epsilon k sigma is less than mu. What does it mean? It means that if we have something like this, if oops, I think this is the dagger, yeah. So if ek sigma is greater than mu, as in like we are talking about a state which is outside the Fermi sphere, there if you add dk sigma dagger, it creates an electron, because then it becomes ck sigma dagger, electron creation operator. But if you are in a state which is inside the Fermi sphere, so ek sigma is less than mu, then it creates a hole. It doesn't create an electron, it creates a hole. So it takes into account both of the excitations, right? Okay, so now we will actually, so this is often called the excitation creation operator. So this will take in both the hole picture and electron picture. So we have ek sigma minus mu ck dagger ck sigma k sigma. So we divide it into two parts. Where k is less than kf. All of these are vectors, by the way. So if k is less than kf, ck sigma dagger is dk sigma, and ck sigma is dk sigma dagger, because now we are talking about holes, plus mu ek sigma minus mu dk sigma dagger dk sigma. Okay, because now we are talking about electrons. So but and holes and electrons both are fermions. So because of their, it's a very jargon property, but because of their like they are indistinguishable, and because of Pauli's exclusion principle, they can't actually uh, take up the same space. Sometimes this is true. This is a well-known fermionic commutation, fermionic relation. So this is one. So this is a called the this is often called the it's a relation found in fermions. Electrons and holes are fermions. Fermion is a kind of particles, kind of indistinguishable particle. So there are only two types of indistinguishable particle: boson and fermion. Okay, fine. So what we do is, if we massage this expression like that, we will get, oops, I think this is k greater than kf, not k less than, yeah, k less than kf minus mm, dk sigma, dk sigma. Okay, so if we do that, then what we get is plus k sigma, k greater than kf, ef minus mu dk sigma, dk sigma. So as we can see, this if we define something like this, an operator like this, then the h will become, and this becomes E naught. This is the ground state energy, because if you understand, then this is actually the ground state energy. It takes into account all of the states which are below the Fermi momentum, or the Fermi energy, and populates them with one electron each, for each spin. So E naught is actually 2 into k less than kf ef minus mu, because there are two electrons per each k, because there are two spins, right? So if we do that, then we will get mm, oops, there is ek sigma, yeah, ek sigma dk sigma dagger dk sigma. So that is how we will actually express the whole Hamiltonian in terms of some ground state energy plus excited state. Okay, makes sense. Fine. So that is the first part, that this is the representation of Sommerfeld model with respect to the second quantization. This is intimately related to what we will do in the second part of this class, which will be released in the next video. Is that we will actually be discussing the concept of density of states. The next episode will be on density of states. We will discuss about why density of states, what is the exact need of density of states, and what is the concept of density of states, and how we can use density of states to calculate a variety of properties of the Sommerfeld model. So it's a general, it's a general uh, tool in a toolbox. So we will have a toolbox of various tools which we can use in calculating the properties of fermionic systems or like Sommerfeld model systems. So in this, so let's do a recap of what we did here. So today we discussed about second quantization of Sommerfeld model. Second quantization is nothing but a language of expressing the properties of indistinguishable particles, a system which has a lot of indistinguishable particles, where we are not interested about what each particle is doing, rather we are interested in how many particles are there in each state. So yeah, that is the difference. We are more interested about the observable and it's like the occupation of different levels of the observable quantity or the state rather than what each particle is doing. So we define the creation and destruction operator which create and annihilate one particle in each state. In a given state, we uh, expressed the Sommerfeld Hamiltonian in second quantization picture, and we also discussed the ck sigma dagger. Ck sigma, this is the number operator, or this tells us the number of electrons or indistinguishable particles in the state k sigma. And then we talked about how like the excitation of this ground state can also be electron and hole. So the ground state is one electron each in every state up till up until the Fermi energy. But the excitation can be removing an electron from inside or adding an electron outside. So it can be creating a hole when the k is less than kf, and it can be creating an electron when k is greater than kf. So that's why we need this Hamiltonian which has only electron creation operator to accommodate also the hole creation operators. So we define the hole creation operator to be electron annihilation operator, and we define an excitation operator rather than electron creation operator, excitation operator. So we discussed about how we can change the Sommerfeld Hamiltonian in terms, we can write it in terms of the excitation operator, and we saw that the excitation operator is given as this, which is like the Hamiltonian in terms of excitation operator is given as this, which has the first term which is the ground state energy and the second term which has the excitation energies, which is always positive, and the excitation operators. In for free electron case, the ek sigma is given as h square k square by 2m as we saw earlier. So we can see that farther you go from the Fermi surface, the larger will be the excitation energy. Okay, so that was and in the next class we will discuss about the density of states and how we can calculate different properties very easily about by using the density of state concept. So see you in the next class and best of luck.